Welcome again on this fascinating journey of learning research. This is the third video of the second chapter. In this video, we are going to discuss about statistical terms in sampling and sampling distribution. Let's begin it this way. A researcher wishes to explore customer satisfaction for a given product. So he's carrying some kind of form with him, maybe a questionnaire, and for let's say in a given questionnaire you find out that for let's say there are 20-30 different questions related with different dimension. Each of them is actually is a kind of variable. So for let's say one such question, the respondent has responded this way. Let's say he encircles 4, and then you collect for the same question, you try to find out the overall average from the entire sample. So whatever could be the size, let's say you in your sample you have 400 people. So for 400 such people, what is the average? You again compute the average and you arrive at this number 3.75. so this thing, whatever you do on your sample, takes you to this statistic. Remember, there is no S to it. Statistic. So you compute a statistic on a sample, but what is the use of this statistic? Ultimately, you are interested in generalization. So for the larger population, if it is possible, if it is at all possible for you to cover each and every member of a given population, and for a given question, let's say this question, and if you compute the average for the entire population, then that would be called as a parameter. So let's say this is a population average. So as you could see, the whole journey, you cannot go and check with each member of the population. Then what is the purpose of sampling? At least sampling is a smarter way to derive inferences about this bigger population. So from this statistic, you tend to estimate parameter. So from sample average to population average. So sample average is nothing but your statistic. Your population average is nothing but your parameter. Make this distinction crystal clear, that how this. So you are into an estimation business. So we tend to estimate how well we could estimate. So how well we could estimate from our statistic to parameter. This is all about our this all reflects the quality of our research work, right? So we arrive at three terms: variable, statistic, and parameter. So let's try to focus on the key terms. Response is a specific measurement value that a sampling unit supplies. So sampling unit is basically, let's say, your respondent. They are supplying a specific measurement value. As you could see here, this person is supplying, let's say, 4 on a given attribute on a given for the given question. So this is actually a response. Now looking across the responses from your entire sample, you arrive at a statistic. That is what this statistic is all about. And the reason why you arrive at a statistic is to get an estimate for the population for which you have sampled. So if it is possible for you to cover the entire population, and then it is not like you are estimating, you are actually measuring the average of the whole population, and so it is not referred as a statistic, it is called as population parameter. So population parameters are largely unknown, and our whole exercise is to estimate this population parameter using sample statistic. So it's a very natural question that arises, that how do we get from sample statistic to estimate the population parameter? So moving from sample statistic to population parameter is a journey, and this journey is not possible, or the pathway is actually the sampling distribution. A crucial midway concept between sample statistic and parameter is sampling distribution. In order to understand sampling distribution, let's conduct a thought experiment. So thought experiment, quite interesting, right? So you are not going to do it in the real world, in the world of your thoughts. So a thought experiment, imagine just that instead of just taking a single sample, you took 3 independent samples. So let's say you are studying, let's say, the behavior, let's say the technical abilities of software professionals in an IT company, and this IT company, let's say it has some 300,000 employees. So covering these 300,000 employees is your population at large, and these people are dispersed. So you took a sample of 300 employees, and let's say in the first count 300 from one department, let's say from one area, 300 from another, 250 from, let's say, the third area, and likewise. So maybe 3 independent samples. So these samples are independent, remember, from the same population, and for each of these 3 samples you will compute a single statistic if or the corresponding samples which you took. So now for, let's say, for one sample you have one sample statistic, for second one you have second sample statistics, for third one you have third sample statistic. Even though all 3 samples come from the same population, you do not expect to get the exact same statistic. The reason is quite simple. Let's say it could be some random chance, maybe some setting there is some kind of difference between one unit or the other, maybe some location, or for some random unknown reason you do not know, you do not expect, it wouldn't be logical to think that so much of similarity is to be found in the responses. Yes, responses would be there, but you could not expect a real exact same statistic. Yes, and this is quite logical. Now for the leap of imagination that you took an infinite number of samples. Now this is something which can be done only in thought experiments, because infinity is a number which nobody has seen, or if you cannot simply attain that. But yes, it is quite likely that you could do that. You can do from the same population, you take sample, you again mix the people, you again take sample, and you repeat this process for infinite number of times. So what you will get actually, for each sample you will get a sample statistic. Let's say sample average. So SA1 comma SA2 sample average 2 dot sample average n sample average infinite. I do not know what this infinite would be, but this is how it is. And each what you are more likely to found if you will try to plot these things, averages on a to get a histogram or bar graph. Let's say this is your, you wish to plot it. So plotting, you will more likely to find that the averages will cluster more to the center, and very few would be there on the extreme side. So something like this automatically will come. So as you go on the extremes, the most of the values would find its place in the central region, and lesser and lesser values will find its place on the extremes. So what you arrive at is you actually do, in this experiment originally we took 3 samples, so we computed 3 separate averages. We get this kind of distribution, but then we replicated this and we tried to do this infinite number of times, and we again plotted this curve. What we arrive at, that huge chunk of data is here in the midway, and as you could see, and as you move to the extremes on both the sides, the likelihood would be less. So getting an extreme value is rare, getting a mid value is highly probable. Try to understand it this way. Getting an extreme value on the other sides is less likely. Getting a mid value, a value closer to the mid value, is more likely. So this is what is called a sampling distribution. It is the distribution of a statistic across an infinite number of samples. So what is the use? Why we are doing this? Let me give you a very small but very helpful example to why we are doing these things. Let me use some different color. Let's say why we are conducting this sampling distribution, to arrive at some shape. Yes, we have arrived at some shape, and shapes have geometry, and these things have geometrical properties. Let's say you have a rectangle, and you know what is the area and you know what is the length. So if you know 2 values, let's say length and area, can you compute what is the breadth? Yes, actually area is equal to length into breadth for a rectangle. So we would be using the same kind of logic once we will start using the sampling distribution. Once we have some kind of assumption that the data which we are dealing with is following some kind of distribution, it gives us something about the shape and properties. Because of its shape, it has certain properties, and we will be using those properties to arrive at, let's say, to estimate the parameter, because that is what we are interested in. We are not interested in sample statistic. To begin with, we are interested in sample statistic, but our underlying idea is to estimate population parameter. Remember this, and with this word I would like to stop here, and we'll discuss more about sampling distribution, and specifically we'll discuss about this bell-shaped curve which is called normal curve in our next video. Thank you.